This is the second attempt to recording this video. I'm just going to do the first 5 minutes or so again because my explanations weren't fantastic and I jumped around a little bit last time. So, talking about networks. Networks are a way of connecting different objects together. This can be towns connected together. So, looking at this example here, we've got a couple of friends who are visiting each other's houses, and there's a bunch of houses. Each of these points are connected by these lines. So it can be towns connected together by roads, it could be computers connected together to a server, or it could be social media, so people connected to each other, social media connections. All right, so just having a look at this example. Dean and Fun are good friends who like to visit each other. So this is Dean's house just here, and Fun's house just over here. There's roads in between them, and there's the distances between the roads. So 3 from here to here, 2 from here to here. The time taken to walk to each road is shown in minutes. Assuming there's no backtracking, how many different paths are there from Dean's house to Fan's house, and what's the quickest route? So obviously we could do trial and error, but the study of networks, or sometimes called graph theory, is a way of using mathematics to solve these problems more efficiently. So we'll first just look at the information around some important terms. I'll go through this one at a time, trying to be quite slow and clear. So firstly, a node or a vertex. The plurals for these are nodes or vertices. So we've got each of these circles. In this diagram, it's each of the houses is a node or a vertex. So just two names for the same thing. Okay, second one. I know it's out of order. Those of you with OCD, just try and relax. Edges are the connections between nodes. So, for example, just here, this is an edge. Arcs I'll come to in a moment. So, second one down, degree. The degree of a vertex is how many edges are connected. So, for this vertex just here, there are 2 edges connected, so its degree is 2. As opposed to this one just here, where the degree is 3. It brings us to odd and even vertices, so just down here. A vertex is called even if it's got an even number of edges. So, even number of edges, this vertex here is even. And that's because it's got an even degree. Whereas this one here is odd. A path. So a path is a way we can move from one vertex to another through a few different in between vertices. So we could go from Dean's house up here, up to here, up to here, up to here, and then down to Fan's house. So the important thing, a path is just a single direction and only moves through each vertex once. So a circuit is similar to a path, but we start at one place and we end up at the same place again. So from Dean's house, I'll just get rid of some of their stuff. From Dean's house, we could move around here, up to there, around here, and then back again. And that would be a circuit. Only moves through each vertex once, and you end up back at the same place. Okay. Weight. So each of these edges has a different number, and in this example, they're minutes. We call that the weight. It's a way of measuring the size of an edge. So it could be in time, it could be in distance, or there are a few other examples. Could be. So next, this one gets slightly more complicated. Traversable. So a network is either traversable or it's not. In a traversable network, we can connect every single node together, only going through the edges once. So if we moved through this network, I'm not sure whether this one's traversable or not, we would need to only touch each edge once. So I'm just giving this a go. Whoop, no, ended up back there. It doesn't look like this network's traversable, but it might be. So if you can move through a network and only touch each edge once, then it is traversable. Okay, last thing, a directed network. Let's imagine for a second that in these roads between Dean's house and Van's house, there is a one-way road. So if you can only move one direction on a network, then it's a directed network. This one here doesn't have any arrows whatsoever, so we would say it's undirected. So if you can move one direction only, so if there are one-way roads, it's a directed network. If you can move both directions on any of the edges, it's undirected. And that just brings me to the last point, just back up here, edges and arcs. So I just said an edge is connecting two vertices together. If it is a one-way network, if it's a directed network, we call it an arc. So we don't call it an edge, we call it an arc if it's a directed network. Okay, continue with the video original. All right, quick example. Draw a network diagram to represent the roads between towns P, Q, R, S, and T. And then there's some distances between them. So we'll just start with, so town P is 23 kilometers from Q and 17 from T. So P connects to Q, connects to town T. Town P is 23 from Q, so the weight of that edge is 23, and the weight of this edge is 17. Town Q is 20 kilometers from town R. So I'll drop down here and say this is town R. 20 is the weight, and it's also 38 kilometers from town S. So 38. And then finally, town R is 31 kilometers from town S. So okay. I'm going to move on to some more terms now. I promise the rest of this has way less this vocabulary. So an Eulerian circuit, this was created by Euler, is a circuit. So remember, a circuit is when we're moving from between vertices and we're connecting up and returning to the same place. An Eulerian circuit is when every single edge is touched and we move the whole way through. So we move across every single edge and return to the same point. Okay, that's Eulerian circuit. Hamiltonian path. So remember, a path is when we move from one location to another across a few different vertices. A Hamiltonian path that connects every vertex, but only once. It doesn't backtrack. Sorry, that's a Hamiltonian path. A Hamiltonian circuit is similar, but it connects every single vertex only once and then returns back to the same location. Excuse me. Okay. A complete graph is when every vertex is immediately next to every other vertex. So another word we use here is adjacent. This vertex is adjacent to this vertex because it's connected with one edge. On the other hand, this one, so that is a complete graph. This one here is not a complete graph because there's a couple of these which aren't directly connected to each other. So this one here isn't connected. Oh, sorry, it's connected to that one. I think I've given you a bad example here. In any case, a complete graph, an incomplete graph will not actually be connected to every single vertex. So every vertex won't be connected to every other one. All right. A spanning tree is just a simple network where there is only a single path between each location. Slight technical issue there. Spanning tree is a very simple network where every vertex is connected by only a single edge. So it's only a single path through between every vertex. Okay, a couple of examples and then I'll see you going with your questions. In this example, Alex is planning to water a garden with an underground watering system which has pop-up sprinklers. A network is to be drawn to show where the sprinklers are to be located. Okay, could this network be considered to be directed? So I'll just do a small sketch. Let's say this is where the water is coming from, so this is the tap. And then there are sprinklers here, 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 and here. So then if we imagined the water coming from the tap to each of these, I would say that yes, it looks like it will be directed network. So we can't have the water flowing back towards the tap. So yes, I would say that it is. What are the nodes of the diagram? The nodes are the sprinkler heads. The edges is the pipe work in between them. So these are pipes. And what problem might Alex be interested in solving? I would imagine that Alex is trying to work out the quickest way, the least pipe that he can use to connect all the sprinklers together from the tap. Okay, next, last question. Model the access to rooms on the first floor of this two-story house as a network. So I'll start with the stairs, connecting to the hall. So then the hall moves off. I possibly haven't designed this very well. The hall moves to a bedroom. Bedroom 1, it goes to a bathroom. The hallway also connects to bedroom 2, but then bedroom 2 is also connected to the bathroom. The hallway connects to the veranda. So in this case, the nodes or the vertices are each of the rooms. So the veranda connects to the kitchen, which connects to, and then we've got the hallway goes to the dining room, but the dining room also connects to the kitchen. And finally, the hallway connects also to the lounge room. Okay, I'll leave you there. So practice some of these in your workbook.